All right, it's a rather drab grey autumn day here in Sydney, so I decided to run with a more colourful autumn background from Japan last year. So that backdrop there is Hachinohe in the far north of Japan. And one of the fun things to do there in autumn is to use your weekends to basically chase the autumn south across the country and just get heaps of really good photographs with really nice color in it. Something you don't really get in Australia, where the trees don't do quite as spectacular a color show as they do in countries like Japan. Okay, we've done overdamped and critically damped oscillators. They're about as exciting as having a bucket of water tipped over your head, but we have to do them as part of mechanics. And now we need to clean up the last part, which is a slightly more interesting problem, actually, the underdamped oscillators, because you get some rather interesting behaviors out. Instead of just having oscillations killed, what you get is systems where you get a little bit of oscillation, a little bit of damping, and these can be kind of interesting to play with, both mathematically and if you're building actual real oscillators. And a lot of cases where you get really interesting dynamics in oscillators, you're actually dealing with underdamped oscillator scenarios. So let's kick back into here, into our underdamped situation. So underdamped, we have c squared minus 4mk less than 0. And so this is, comes back to our discriminant, which we identified earlier as the thing that tells us the characteristics of the different solutions to the quadratic leading term in the equation of motion. And so here we get two solutions, and the solutions are complex, and now you'll see why they're complex. So we have Q1, and it will be minus C on 2m, which is always real, so it's the real part of this complex term. And then the square root from the quadratic solution gives you the complex, the imaginary component. So this is now I k on m minus c squared on 4m squared to the half. And likewise, there's a Q2 term in here as well, minus c on 2m minus I in this case, k on m minus c squared on 4m squared, like so. Okay. And so you'll notice both of these are actually complex numbers. Now, in the underdamped situation, what we do is we start to introduce some new variables to clean this up. And so one of them is we introduce a gamma. And again, we'll call this C over 2m, okay? And we're not going to split gamma off to gamma 1 and gamma 2 to tie to Q1 and Q2 in this particular case, just because it's not an effective way of solving the problem. We're also going to introduce a solution that we had from yesterday. We're going to call omega naught square root k over m, okay? And this is the main reason why I went back and did simple harmonic motion yesterday, because I wanted to be able to pull relations from yesterday's case. You'll probably spot where I'm heading with this. If I look at this term up here, I've got a k on m and I've got a c on 2m term up here. And so what I can do is write an omega d in here, which is basically just square root k on m minus c squared on 4m squared. Okay, so in other words, I'm just calling it this term here, and it is going to be square root of omega naught squared minus gamma squared, okay? So I'm using gamma slightly differently here to what I did in the overdamped case, because in the overdamped case there's just no oscillations, and so it's an easy way to go. I can now write Q1 and Q2 in terms of these two new variables I've got, right? So Q1 becomes minus gamma plus I omega d, and Q2 becomes minus gamma minus I omega d in this particular case, okay? And so if we're working on a trial solution here, we would probably be inspired by both what we did earlier in the overdamped case to make sure we have two terms to correspond to the two different roots of the quadratic. And we would also possibly be inspired by what we did yesterday to realize that these two things will have prefactors at the front that are probably complex and very likely to be conjugates, okay? So what we're going to do here is call this C plus E minus gamma plus I omega d t plus C minus E minus gamma I omega d t, like so. Okay, and at the moment all I'm doing is specifying that C, the two prefactors are likely to be complex by calling them C, and I'm attaching a plus and a minus to them not because of any expectations other than that I want to associate the plus term here with the plus exponent and the minus term here with the minus exponent, right? Later on, we would probably guess at this stage that they're likely to be conjugates, but we're not going to force that, okay? Again, this is one of these things in physics where sometimes your instinct is useful to solving problems. Your instinct may be right, your instinct may be wrong. You'll find that out eventually, but the game sometimes it's just useful to have an instinct. The two exponentials we have here, because of the sum in the top, we can split them, right? You'll remember that EA plus B is EA times EB. So we can actually factor the real part out to the front and keep the complex part off the side. So we would write this thing as E minus gamma T of C plus E minus I omega d t. Actually, this one will be a plus just here. Plus C minus E minus I omega d t over here. Okay? And you'll notice straight up something quite interesting here. This is just an exponential decay. And this is an oscillation. And what we basically have here is a product of a wave and an exponential. And if you take the product of a wave and an exponential, you get something that looks a little bit like this. So if you plot x of t as a function of t, you get a wave that basically decays as a function of time. And you can draw what we call an envelope function around it. So this is this dashed line down here, and this dashed line is basically the E minus gamma t term that we had, and then your wave will oscillate inside that envelope towards the decay point. And the one other thing that you will notice in here is that the period of the oscillations up here is WD not, omega naught, omega d, not omega naught. And so what we have happening here is a change in the period of the oscillation. So we have our damping term, or contribution from our damping term gamma just here, basically affecting the oscillation wavelength or oscillation frequency of our system. And so damping basically causes the oscillation to be slower than it would be undamped. So in addition to losing energy, we basically get a slowing down of that oscillation. And the easiest way to think about that is you can imagine a system without damping just oscillating side to side. And the damping is actually trying to impede the motion. So you can almost imagine having to try and move through molasses or something. So it kind of has to fight this resistance, which is going to slow it down, and that means the frequency gets less. Okay, so physically we can make sense of this in the mathematics that we get in this particular problem. Okay, And what we find in this particular situation is that in one period of oscillation, our amplitude decays by E minus gamma TD, okay? Or another way to put this is in time, gamma minus 1 equals 2m on C, amplitude drops by 1 over E. Okay, we get this nice exponential decay behavior. What's interesting here is that we can take our underdamped situation and we can break it up into two separate classifications, right? You can imagine in terms of the graph that we've got on the slide here straight away that there would be two different cases you can imagine, right? One is where the damping is very, very strong. You can imagine this exponential cuts in very, very strongly and on a very short time scale. And so our oscillation, while it doesn't do what you have in the critically damped or overdamped case of basically just quenching the oscillation entirely, you only get one or two oscillations in before it's died out, okay? And so the case I'm showing here is essentially like a strongly damped case where it only takes one or two periods for the oscillation to wind down. The other case you can imagine is a weak damping case where that exponential is very, very long time tail. And so you have oscillations, but you're basically just letting those oscillations wind down. And one of the really good ways to think this is if you have a really, really good pendulum on a very good frictionless axis, you can kick this thing off and it will oscillate backwards and forwards. And it's essentially a damped oscillator. It's a damped oscillator because you've got air resistance term to the swing of the arm, and you also have a tiny bit of friction and pivot point. And so it will gradually die its way down, but having done, you know, hundreds or thousands of oscillations before it finally drops away to zero, okay? So you can imagine we really might be interested in these two particular cases because one might be very interesting for just damping oscillatory systems quickly, and the other one might be, you know, how do we minimize damping so that we can, you know, stop a pendulum from running down quite so quick. Imagine you're a clock designer and you want to try and minimize the fight you have to have against damping in your system so that you can actually the main reason there that you would want to try and fight your damping is because if your oscillation period is determining, you know, your time like it is in a clock, then the stronger the damping, the bigger the discrepancy between the actual oscillation time and the desired oscillation time for your system, so the less accurate your timing system would be, okay? So we can break these down into these two particular cases, and we'll call these 3A weak damping, and 3B strong damping. All right, so in the weak damping case, you have omega naught is much bigger than the gamma term, as you would expect in here. And if you do take that case, then this becomes a if this is small, it becomes a small number, and so we basically end up back towards omega naught. And so what we find is our omega d here is roughly equal to omega naught, okay? This is the case where the tail is very long and the oscillation is continued for a long period of time without very much change in the frequency of oscillation. And then the strong damping case, what we have is that gamma basically heads towards omega naught, and in this particular case, we get our omega d going towards zero, okay? And you'll notice here that we have an implicit limit on omega naught here, because on gamma, sorry, here, because if you make gamma sufficiently large that it becomes omega naught, then omega naught squared minus omega naught squared is 0, and so the period goes essentially to infinity, right? If you make gamma bigger than that, then you end up in the case where this term in the bottom here is negative and the system no longer makes sense. And I'll let you check for yourselves that this basically corresponds to the limit where you drive strong damping up against the critical damping limit and you switch off the oscillatory solution, okay? When I was an undergraduate, this was basically one of the problem exercises, was take the limit of gamma becomes, approaches omega naught and becomes larger. What is the behavior of the system, okay? I'll let you work through that one for yourself as an exercise. All right, so we've got that built together, and where I want to go with this for the remainder of this hour is to look at the energy diagram and the phase space diagram, same as we did yesterday for our simple harmonic oscillator, because what you want to do is consider this both for damped and then forced oscillators, and then later on if you do sort of chaotic systems, and one of the experiments in the undergraduate lab is essentially a chaotic pendulum, you kind of need to build these ideas one on the back of the other, and oscillator systems, understanding their phase space and energy behavior is actually a really useful thing, okay? So let's do it, but we're going to do it with a focus on the underdamped situation, because the overdamped and critically damped situations are not quite as interesting to look at, okay? So we have a total energy here, E, and it's going to be T plus V, and it's a rather simple thing. We've done it to death in the last few lectures. So it's a half mx dot squared plus a half kx squared, like so, okay? For an undamped oscillator, our total energy in the system is constant, right? And we had this yesterday. We drew graphs where we had E as a function of position, or E as a function of time, and they're completely flat and linear, okay? What we have in a damped oscillator system is clearly the energy is changing, right? We put a certain amount of energy in this system to start and let it keep oscillating. And if we have a simple harmonic oscillator where we ignore any sort of dissipative terms, then it will keep that total energy fixed all the way through as a function of time. What we have here, whether it's overdamped, in which case the energy's gone very quickly, or it's weakly damped, in which case it just sort of gradually winds itself down, is a total energy that's kind of decaying as a function of time. And that total energy is basically just lost. It's lost to pushing air around, it's lost to generating heat by friction in the pivot. In a spring-based system, it might be lost to friction in the surface that it's sliding on, or if you had an eddy current damper, it would be lost to I squared R, heating of the metal in the damping plate, okay? And so for damped oscillations, E is not constant, and so dE on dt is meaningful. And so we can work out what this thing is, right? So let's play around with this. We'll start with dE on dt here. So this would be d on dt of a half mx dot squared plus a half kx squared. And I'm going to take a step that I would normally just jump straight over if I was doing this as a problem or in an exam, but I just want to make it really clear that I'm not just taking the square and cancelling out the half here. There's actually a product rule thing going on here. So what we've got up in this term here is basically mx dot x dot, and what we've got here is kxx, right? And so this thing here is basically a half m. I have to take the derivative of the first one, right? So x double dot x dot. And then I have to take the derivative of the second term. So this will be m x dot x double dot, okay? And then the same thing happens with the term on the end. So it's a half, a half k x dot x plus a half k x x dot. And then when I add these up, I get m x dot x double dot plus k x x dot. Okay. Whenever I've shown this, done this derivation in the past, and I jump straight to this this line, everyone's like, "Hang on, 2 cancelled out the thing, so why didn't you just blah?" Okay, so just to make that really clear what that step is there. And of course, you'll notice there's a common factor here, which is x dot, so I can pull that out the front. So this will be x dot m x double dot plus kx, like so, okay? I'm going to call this 1 for now, just so I can keep track of it later on, okay? We can go back to our equation of motion that we had at the start of the problem, which looked like this. So I don't have to scroll back up. Plus cx dot plus kx equals 0. And I can split the cx term off the end. So what I can do is write this as mx double dot plus kx is equal to minus cx dot. And let's call this 2 for a moment. You'll notice that this thing here is this thing here, okay? And so what I'm going to do is swap that part out by joining those 2 things together. So I can substitute 2 into 1. And what I would have here is basically dE on dt is equal to x dot times minus cx dot, which is basically minus cx dot squared, okay? And so what we have here is the energy loss as a function of time depending on the square of the velocity of the system and our damping term. And then the minus here basically just says that that energy is going to decay, right? It's telling us it's not increasing, which would be a positive term in there. Okay, so if you want to, you can integrate backwards and just double check that this whole thing hangs together really well in here. But we end up with a term that looks like this, okay? All right. And if you imagine taking a limit where c is 0, in other words, we switch the damping off, then dE on dt is 0, and we get back to our constant energy term, okay? So basically this equation in here is telling us that while ever the system is moving, in other words, x dot is not equal to 0, if c is finite, then the system will lose energy, all right? That's what this equation means. Sort of an energy damping equation. And so we can finish off here basically just looking at the graphs of for this. So one thing that you can do in here, and it's not in my notes, but you can do it, would be to integrate with respect to t, okay? And this would then get you energy in here in terms of time, and you end up having to solve a differential equation out for this, and you'll get some plot. I might do this as an extension in a future year because it's not even done in the textbooks, and you get your energy decaying out, okay? I might leave that one as a little exercise. But the interesting thing to do in here is to look at your phase space plots in here. And so rather than sketch them up, I might use my own notes in here. So what you get is, rather than the neat ellipses that you had for the simple harmonic motion phase spaces that we showed yesterday, you get situations that look a little bit like this. So if you imagine your overdamped oscillator, this point up here would be part of an ellipse in here that would correspond to your simple harmonic motion that you had yesterday. And imagine you get to this point of the motion and you just immediately kick in overdamped scenarios. So if you go back to the setup we had at the start of the problem, spring, mass on a frictionless surface connected to some eddy current thing, you could imagine flipping a switch that turns the magnetic field on, and that immediately kicks in the damping at a particular point in the oscillation, right? What would happen there is basically the system would, without oscillating anymore, drop down to zero, which means it would no longer continue on this elliptical orbit. It would basically just head as quickly as possible, just straight into zero, okay? And so you get a velocity phase space that looks like this, not very interesting. If you consider your weakly damped situation here, now what you would have is, you can imagine having an ellipse in here going around. And so what happens is you still maintain your oscillation, so you're still sort of going around and around and around here. And you remember we talked about this yesterday. The position here corresponds to moving through the center of motion with velocity. This corresponds to getting to the end of the motion and turning around and coming back. So you can imagine this is sort of moving through, get to the end, come back a little bit less, a little bit less, a little bit less, a little bit less, decay yourself down to zero. Okay, and so that would be this spiral that comes in through a series of ellipses and ends up basically back at the center of the motion. All right, that was pretty much all I had today from the mathematics side, but it's very easy to do these sorts of problems and be missing some context. And so one of my favorite cases where damping is important is this situation.
On November 7th, the bridge suddenly went into a twisting motion. The wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration with a period of 5 seconds. A professor of engineering went out to see what had happened. He's coming back, walking with some difficulty along the nodal line, which is the center stripe of the roadway.
Okay, if you watch on further, you'll see that the bridge ultimately destroys itself and falls into the sea. Unfortunately, a dog gets killed in the process, which is not very nice. And it highlights a couple of really useful things here. One is it's very easy to say at the end of part of a course like this, oh yes, but you know, I'm an engineer, I'm not a physicist, why do I care about damped oscillators? Actually, as an engineer, you care about damped oscillators a lot. If you're dealing with sort of structural engineering like this, you basically want to stop a system from oscillating and destroying itself. If you're designing, for example, cars, you're building suspension systems, and the whole point in that suspension system is to try and sit as close to the critically damped situation as you can, so you can knock out oscillations, as stop the car bouncing down the road, and to do so in such a way that you manage the fact that sometimes it has a heavy load in it and sometimes it doesn't. The M term changes in that system. If you're dealing with aeronautical, for example, you're dealing with the same thing with planes bouncing around, and you get lots of situations where oscillations can be set up in those sorts of systems. If you're dealing with electrical systems, you get ringing in circuits, you get sort of oscillatory feedback in circuits that you need to damp out. If you're working as a physicist for a living, you can have different parts of your experimental system vibrating one with respect to the other, and you have to worry about damping systems. So if I think back to when I was a PhD student, I had a very large fridge that took samples down to fractions of a degree above absolute zero, and it was suspended from a frame hanging from the ceiling. And when you get down to those sorts of temperatures, the vibrations that you get from just motion in the room through to the fridge on its mount swinging backwards and forwards and so forth sloshes the liquid helium around. That sloshing of the liquid helium around turns up as a temperature rise down in your sample, and so you end up having to, for example, build air cushion systems to try and knock out those vibrations, both to get the temperature down, and also if you're doing electrical measurements, for example, you've got a sample in a magnetic field. If that sample's moving in that magnetic field, you get currents, and you can detect those as well. So often we really care quite a lot about damping systems, and in particular optimizing from underdamped scenarios to critically damped scenarios, or overdamped scenarios to critically damped scenarios, or whatever. If you're a clock designer, you want to get rid of damping. If you're designing oscillatory circuits that oscillate for a long time, you want to get rid of damping. If you're designing something that you don't want to oscillate, you want damping done really well. Okay, so damping really matters. It's an important thing. And then just to finish off with this one example I have here of Tacoma-Narrows Bridge, since we're going to be talking about resonance in the next lecture, and I don't want to show the same video twice, there's a big fallacy that goes around, and it's actually published in a whole pile of textbooks, that the reason why this bridge fell apart was resonance, and it's actually not true. The crucial thing with resonance, as you'll see in the next lecture, is that you need to be driving the system at the same frequency, or very close to the same frequency that it's oscillating at. And if you think about this bridge, there's a wind flowing past it, and that wind is essentially just a constant breeze. It's not like the wind speeds up and slows down at the same frequency as the oscillation is going, or it's blowing up and down at the same oscillation that it's going. Those of you who are doing or have done aerodynamic engineering at some point will know what's going on with this bridge. It's a thing called aeroelastic flutter. It's basically the same thing as when you grow up as a kid, you take a blade of grass and you blow across the blade of grass and you get a whistling noise. And what's happening is just, it's an dynamical instability in the system in response to an airflow past it. You basically generate lift on one side, which then kicks off the other side being the lift generating surface, and you just generate a system like that. And so the thing that destroyed Tacoma-Narrows Bridge is not resonance, it's not forced oscillator, it's the system was not properly damped against just oscillations that happen that are not a resonant oscillation, okay? Just want to clear up that fallacy because it floats around in a lot of books, and do it in such a way I don't have to show that video again. So that sort of finishes up today's lecture. I'll leave sort of integrating back from D on DT to get what the energy versus time looks like for that problem as an exercise, and I might follow up in my notes with in my technical notes with that later with a solution for it for those of you who want to give it a go, and I'll see you next time.